Are recording now. So today we are talking about types of bonds. So two types of bonds that we're going to focus on the most is ionic and covalent bonds. That's what we're going to spend a lot of our time on. So we look at our LAQ. This is a question that we're going to answer with this unit. First question we're going to answer in this unit. How and why are compounds formed? And how does the bond type determine a substance's properties? There are two big takeaways that we're going to pick up today. You don't have to write these down immediately. We're going to see them again. Atoms form bonds so they lose energy to become more stable. We're going to shed electrons in order to interact with other elements to make our elements more stable. And we're going to notice another pattern. Atoms form bonds so they can get a full valence shell of 8 electrons. Why? Because our noble gases are our most stable elements. There's a reason why they don't interact with anything. Because they're stable. They don't need electrons. They don't need to share electrons or lose electrons or gain electrons to gain the stability. They're already there. And we're going to see when we are making bonds that these 2 points are going to be big driving points. So like I said, you don't have to worry about writing it down right now because you're going to see it again on another slide. So in your notes, we want to start first looking at magnesium. So this should be a little bit more of a practice for you. I'd like for you to write down the electron configuration for magnesium, and I want you to circle their valence electrons. Because I remember where my s orbitals are, my p orbitals are, my d's, and my s orbitals are, magnesium is going to fall into which of our 4 orbitals?
3s2.
3s2. It's my last orbital, right? Write that out. So 1s2, 2s2, 2p6, 3s2. Now, magnesium is in group 2, so how many valence electrons am I expecting to see?
2.
Which ones are they?
3s2.
3s2. Circle those guys right there. Now, magnesium, being a very reactive metal, wants to form bonds. To form bonds, it has to get 8 valence electrons. It has 2 already. So if magnesium were to steal or share electrons, how many electrons would it need? 6. It would need 6, right? The goal is 8. I have 2, so I need 6 electrons, right? Whether I steal them, where I share them with another element, I need 6 to get to the outermost electron shell to 8. What if I lost electrons? How many electrons do you think magnesium would have to lose to get to an outer layer of 8 valence electrons? What was it? If I'm looking for 8 valence electrons, what happens if I get rid of the 3s2 orbital? How many electrons do I have in my outermost shell? If I get rid of my 3s, my outermost shell is which orbital? N equals 2, right? How many electrons are in my N equals 2? 8. Magnesium has really 2 options. Magnesium can steal or share electrons with, can share 6 other electrons with something, or it can end up losing 2 electrons and still getting to that more stable energy level. Which one do you think is going to be easier for magnesium to do? To steal 6 electrons from something else, or to lose 2 of them? Which one do you think is going to be the easier route for magnesium? Steal 6 or lose 2?
Lose 2.
Lose 2. In a little bit, we're going to talk about a certain trend that we're going to see. When I look at metals, my metals are always going to lose their valence electrons to become more stable, and my non-metals are going to gain electrons to become more stable. So we did one together. I want to walk around and I want you to do aluminum. I want you to do the exact same thing. I want you to write out aluminum's electron configuration, and I want you to circle the valence electrons. Good practice from what we did from Unit 3. Then, with those 3 ideas, steal, share, or lose, I want you to tell me how many electrons aluminum has to share or steal from something else. How many electrons aluminum has to lose to get to that 8 valence electrons in that outermost shell? Lily. I know you're awake. You haven't been asleep that long. It takes humans at least 40 to 45 minutes to get into REM sleep, deeper to sleep. Especially if you just came back from lunch and I saw you walking and very conscious. This is good signs.
You shouldn't be taking naps. You shouldn't be napping while we're teaching the lesson.
So I know like this section right here, yeah, just have to walk away. All right. So I saw some good stuff out there. If I'm looking at the electron configuration, based on the location of aluminum, I know I'm going into a p orbital. Which p orbital am I going into? 3p1. So 1s2, 2s2, 2p6, 3s2, 3p1. All right. So if I got 3p1, how many valence electrons does aluminum have? 3. I can do it 2 ways. 1, my 3s orbitals aren't full. And 2, I see aluminum is in group 13. Remember, group 13, if I take the 1 away, that tells me how many valence electrons I have. I should see 3 valence electrons. You can circle each one separate. That's okay. I'm not going to be too picky about that. But the fact that we have the 3 S's and the 3P, that's what I'm looking for. Now, I said that there are 3 possibilities. I can share, I can steal, or I can lose electrons. Aluminum. How many electrons does aluminum have to steal or share with somebody else to get that 8 valence electrons? 5, right? I got 3 already. 3 plus 5 is 8. Hey, that's the number I'm looking for, right? How many does that have to lose? 3. If I lose these 3 valence electrons, 2s2, 2p6, 2 plus 6 equals 8. I still hit that same number. We're going to spend some time doing some review with this today. So our goal today is to talk about, to talk about ionic and covalent bonds, and then we're going to make some ions because that's where the ionic part, the ion is where the ionic bond comes from. So what's driving all this? How do I know that my metals are going to lose electrons and my non-metals are going to gain electrons? It all comes down to that trend we talked about last time. One of the three trends, electronegativity. Electronegativity. So we're going to review. So quick definition of electronegativity is how hard an atom pulls on a bond. That's the big thing. How hard the atom is going to pull on those bonded electrons. So if I draw a little map here, do my little quick drawing of my periodic table. Which way does my trend go for electronegativity? What are the two directions that we talked about?
Left to right.
Left to right, it increases. Is it top to bottom or bottom to top? Bottom to top. Or if we just want to draw one arrow, we start from the bottom corner, bottom left corner, all the way to the top right corner. That's my trend for electronegativity, right? That's the one we talked about in Unit 3. That's going to lead us to a very easy trend that we can follow, where let me slide this up. My metals are always going to lose the valence electrons, and my nonmetals are going to gain valence electrons. Especially when we're talking about ionic bonding. Someone's got to steal an electron. Someone has to give up an electron. At that point, one becomes more positive, one becomes more negative. That's our goal here. If we know this trend starting out, we're going to be in a good place. I see some pencils out. I'll give you guys a little bit more time. Make sure you got that. You don't have to draw it exactly as I do. You could just do like before, guys. Remember I was just doing the box?
We don't even have that section.
Might be something you need to take notes on then, sir. Might as well write it on somewhere else. Because remember, it's just review, right?
Yeah.
So if you want to record that, you got to write somewhere on your notes.
Metals, electrons, non-metals.
But that's all right. We're going to talk a lot more about that in a little bit. All right, guys. I'm moving on to the next one. So this isn't something that you have to write down. This is kind of just a bit of review of what we've talked about so far. So the reason why our atoms want to bond to things is because it lowers their energy state. If you have incomplete orbitals, you're more likely to interact with stuff. That's not where the atoms want to be. The atoms want to be like us. They want to fall into a groove. They want to be lazy, like we do. They want to be in that lower energy state. Being in a high energy state is not great long term. Atoms are most stable at their lowest energy state. And how do I get that? By getting that full valence electron shell. And what should be reviewed for you, number 4 and 5 here, in ionic bonds, atoms are going to either gain or lose electrons to become more stable, while covalent bonds, the atoms are going to share those electrons to become more stable. So, like I said, not something you have to write down. This is kind of more just something here to kind of help drive what we're going to be talking about. Now, this leads us into our octet rule. Because we keep seeing that number show up time and time again and again. 8. I want 8 valence electrons. I want 8 valence electron. Octet is another way of saying 8. And we're going to watch a little video to help us see this. Now, in your notes, I do have a section that says octet rule video notes. I'm going to pause it at a certain section that you definitely want to record. If you find any other information in the video helpful to you, I'd write that down as well. But there is one part of the video that's going to be super, super important for you to record.
I want to talk to you guys about...
Hold up now. I'm not ready to talk to him about octet rule yet. There we go. All right. So 3.5 minutes. I'm going to cut the light off. And like I said, there's going to be one part where I'm going to pause it, and you definitely want to record it. Ma'am. Absolutely.
about a basic rule in chemistry called the octet rule. So we know that atoms love to be stable, and the way an atom can achieve stability is by having a complete number of electrons, valence electrons, in the outer energy level. These valence electrons will allow atoms to have different properties. The octet rules state,
right there, you want to make sure you have this. The octet rule is an atom will gain or lose electrons in order to obtain those 8 valent electrons in their outermost shell. In other words, the elements want to reach an electron configuration of the nearest noble gas. Remember, our noble gases are our most stable elements on the periodic table. That's where they want to be. We're going to get some experience with that today when we go through our coursework. That's also going to bleed into our homework. We're going to do a couple of them together for classwork, and then you guys are going to finish the rest by yourself for homework. It's not a lot. It's going to be like 7 or 8 of them that you're going to do. That's just going to help us kind of cement this idea about how we form our ions.
states that an atom will gain or lose electrons to obtain 8 electrons in its outer shell. In other words, elements want to reach an electron configuration of the nearest noble gas. The word octet means a group of 8. For example, an octopus is an animal with 8 legs. An octagon is a shape with 8 sides. So let's look at a model of an atom. We know that an atom has a nucleus, where the protons and neutrons are located. Around the nucleus, we know that there are electron shells where all the electrons are located. The first electron shell in an atom can hold 2 electrons maximum. The electrons in the outermost shell are called valence electrons, which determine the properties of the atom. The second electron shell can hold a maximum of 8 electrons. In this case, the electrons in the second electron shell are called valence electrons. The third electron shell can also hold a maximum of 8 electrons. In this case, the electrons in the third electron shell are called valence electrons, and so on. So let's look at the element lithium. Lithium is in group 1 of the periodic table, and since it's in group 1, it has 1 electron in its outermost shell. Another example is an element that is in group 16 of the periodic table. It will have 6 valence electrons. Elements in the same column as group 16 will also have 6 valence electrons. This is a general way to figure out the number of electrons for an element. Elements like to be in their most stable electron configuration. So the easiest thing for lithium to do is lose that 1 electron in its outermost shell to obtain the electron configuration of the noble gas helium. Helium is a very stable element because of its electron configuration. Sodium, like lithium, is also in group 1 and has 1 valence electron. Notice the lonely valence electron in the third shell of the atom. This shell needs 7 more electrons to satisfy the octet rule, but the easiest thing for sodium to do is lose that electron if it can. And when it does, sodium will now have the electron configuration of the noble gas neon. Now let's look at chlorine. Chlorine is in group 17, which indicates it has 7 valence electrons. So looking at the chlorine atom, notice how the outermost shell needs 1 more electron to satisfy the octet rule and have 8 electrons to be stable.
Sure, pay attention, right?
That's why chlorine is a very reactive element, because it just needs 1 more electron. And when it does, it will have the stable electron configuration of noble gas argon. And that is the octet rule.
All right. Far out with the octet rule. So, now that we've kind of given the background of what our atoms want to do, now we're going to talk about our 2 main types of bonds, our ionic bonds and our covalent bonds. That's our goal now. There we go. All right, so this one, perfect. So, ionic bonds. Bonds that form between electrons when electrons are transferred. So, when you are talking to me about ionic bonds, this is a word I'm definitely going to be looking for. Transferred. What does that mean? It means that somebody's ripping off an electron from somebody else. Now, for this to happen, our atoms have to have very different electronegativities. So remember my pattern. What's my pattern for electronegativity? Goes top to bottom, so bottom to top, and then left to right. So it's going in this manner. So, if I'm looking at my periodic table, I need 2 very different electronegativities. I see my metals. My metals have very low electronegativity, right? So this is going to occur between metals, low electronegativity. And what other groups have we talked about? We talked about nonmetals, and we also talked about semimetals, metalloids. So which one is going to be the other that's very high? Which one has very high electronegativity? Nonmetals. The nonmetals have the very high electronegativity. So when I see ionic bonding, I'm always going to see a metal and a nonmetal. Push this up a little bit. So an example of this would be lithium plus fluorine would give me lithium fluoride. Which one has the lowest electronegativity? The lithium or the fluorine? Lithium would, right? So that means fluorine has to have the high one, right? Lithium has 3 electrons around it. 3. Fluorine has 1, 2, 3, 4, 5, 6, 7. Fluorine is going to pull this electron over to fluorine, making my lithium slightly positive, making my fluorine slightly negative, creating what we are going to call ions. Now, when we pull, we're going to put names to these positively charged metals and negatively charged nonmetals. We're going to mention them today, but we're going to dig a lot deeper into them next time I see you. But the key thing, if we walk away today knowing that my metals have low electronegativity and are going to lose their valence electrons to the high electronegativity nonmetal that's bonding to, we're in a good place to be. See some writing? We'll give you guys a little chance to write that down. While that's going on, I'm going to do a quick thing. We ready to move on, guys? Give me a quick second. So I'm going to flip over to the next one. So now you're going to talk about covalent bonding. I'll give you guys a head start on that one. So covalent bonding is where I'm going to share those electrons because both of my atoms have high electronegativity. All right. So who do we said? If I look at my periodic table, once again, we said my arrow points that way. So which groups on my periodic table have the high electronegativity? My metals, my metalloids, or my nonmetals? Nonmetals. So both have high. So both are non-metals. So my covalent bonds are only going to work between my non-metals. Our example is going to be carbon and fluorine. Both are nonmetals. And both are going, and they're going to form CF4. My carbon starts off with 4 valence electrons. 1, 2, 3, 4. Why didn't I want to use H? I wanted to use F. I wanted to use fluorine. Fluorine does the same thing. Oh wait, no, it doesn't. H. You're right. I'm dumb. They're H's. 7. That's wrong. I'm thinking of something else.
You just got methane.
What's that? Because it occurs between metals and nonmetals. Nonmetals and nonmetals. Covalent bonds only happen between two nonmetals. So one nonmetal and another nonmetal make up a covalent bond. So in my example, I made a small mistake. Fluorine is going to want to make a couple bonds. So that's why I switch quickly to hydrogen. Carbon and hydrogen are both nonmetals, making methane CH4. That's an example of my covalent bonding. Two nonmetals reacting with each other. Now, when it comes to a test or quiz, we have to be able to compare and contrast each one. So, here is your comparison and contrasting. My ionic, my electrons are transferred. Big thing, they are transferred. In my example, sodium and chlorine, making sodium chloride. Which one had to lose electrons? Who lost electrons? Was it the sodium or the chlorine? Who lost? So Na plus Cl, who had to lose electrons in this relationship? The sodium does, right? Sodium is, so it's going to lose one of its electrons to chlorine, making the sodium positive, slightly positive, making the chlorine slightly negative. Because we're going to have these charges, we're going to say everything in a ionic bond, everything's polar. When I'm looking at covalent, I'm going to share those electrons. Oh, there it is. Electrons are shared. Now, we haven't gotten into the idea of polarity yet, but we will be getting into it shortly. So I'm giving you a little heads up of what we're going to be doing later in life. Where my ionic is always polar, my covalent can be either or. When I see you next time, we're going to see how well a covalent bond and an ionic bond can transfer electricity. Is there something going outside, Christina?
No.
I'm just curious why you keep staring at my door.
Oh.
We're going to see certain relationships. Now, one thing that they both end up going for is that the goal is to fill that outer valence shell. That's the biggest thing both ionic and covalent are doing. They're always trying to fill that outer valence shell. They just have different ways of doing it. One is we're stealing and giving away electrons. The other one is we're sharing those electrons. That's the big difference here. And we're going to see our covalent bonds. We're going to get into the concept a little bit in this unit about single, doubles, and triple bonds. So when we think about carbon dioxide, that has two double bonds. Carbon's nonmetal, oxygen's nonmetal, boom, that's a covalent bond. If I look at, I need a periodic table real fast so I can just kind of like throw some things together real quick. if I see, let's go. Let's see what's an easy one. Li2O. Li knows lithium, it's a metal. The oxygen's non-metal. I know that that's going to be an ionic bond. Just by looking at the parts, I know what's going to be. That's our goal. Now, on the last page of your notes, it's kind of more just like a graphic organizer to help you out. Reminding you of your different stuff. Ionic bonding is always formed between a metal and a non-metal. The electrons are always transferred. Someone's having their electrons ripped off from each other. It's very important that we know where we find our metals and where we find our non-metals. So on your periodic table, you see this bold line looking like stairs going down. This line separates my metals from my non-metals. The items that sit on the steps are my metalloids. We're not going to mess with the metalloids too much in this unit because the point of a metalloid is that it can either act as a metal or a non-metal. They make things weird. So we're going to strictly stick with the metals, which is the majority of my periodic table, and the non-metals, my top right corner, where I see all my highly electronegative elements. Give me a second. That is what we're going to focus on. Now, what I am going to do is I'm going to pass you the classwork/homework that we're going to focus on today. Because we got 40 minutes before the bell rings. 2:02 was when you're leaving here, guys. So we have a lot of time to work on this. If we get this done beforehand, great. Hold on to it and bring it with you the next time that you're here. Because it's a lot easier for me not to lose your papers if you hold on to it. So I got Christine going first. Sure, that's fine. So make sure you have your periodic table next to you. It's going to make your life so much easier on this part. But here we are going to talk about, a second. There we go. So, forming ions. So we're mostly focusing right now on ionic bonding. So first one that we're going to focus on is ions, and then as we get into covalent bonds, we're going to get into drawing our bonds, such as Lewis dot models. That's the things that we're going to be doing after we come back from winter break. But looking at the top here, forming ions worksheet. When atoms react, they often gain or lose electrons to form ions. Typically, they will lose or gain enough electrons so they have 8 valence electrons. Otherwise, we're just talking about the octet rule all over again. We're always aiming for 8. Oh, Lord. Which makes the ion stable like the noble gases and gives them this electron configuration of the nearest noble gas. So when I looked at magnesium and I lost 2 electrons, if I looked at my periodic table, the closest noble gas to it was neon. When I lose those electrons, I'm on the same electron configuration as neon. Metals will always lose all their valence electrons, which gives them the same electron configuration as the previous noble gas. We're going to walk through 2 examples of that in a second. Since they lose negative electrons, they become positively charged. Now, we're going to add a vocabulary term for positively charged, and that is a cation. We're going to get more into cations next class. Right now, we're just identifying that there is a definition, a vocabulary term that's going to define what we're going to be talking about. Their charge is shown by writing the element symbol again, followed by a superscript sign and a charge. So it gives me the example of calcium. So I flip my paper over real fast. I'm just give you an example here. So we have calcium. Calcium is number 20 in our periodic table. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's my electron configuration for calcium. Calcium is going to lose these 2 electrons when it makes an ion. Making this my electron configuration for Ca plus 2.
Why is strontium featured there twice?
Because I made a mistake.
Should we just cross it out then?
No, you do it twice. So I count my electrons. 2, 4, 10, 12, 18. I have 18 electrons. Which noble gas would have 18 electrons? Helium, neon, argon, krypton, xenon, or radon? Argon. So 1s2, 2s2, 2p6, 3s2, 3p6.
Refer it to the original.
Give me a second. 3p all the way from 1s2 to 3p6. That's my electron configuration for calcium plus 2. It's also my electron configuration for argon. That's what we're going to do today. We're going to identify the element. We're going to identify how many valence electrons it has. We're going to say whether it's going to gain or lose those gain other electrons or lose those valence electrons. Identify the charge it makes. Excuse me. And lastly, which electron configuration does it match in our noble gases? Because if I look at it this way, so calcium has 20 protons because it's atomic number 20. Remember, my atomic number gives me the number of protons. In a neutral case, I should have 20 electrons. 20 minus 20 is going to be what? 0. No charge, right? It's on the house. There's no charge. If I lose these 2 electrons, I still keep 20 protons, right? Because my number of protons identify what element I'm looking at. Minus 18 electrons gives me what? Positive 2 or negative 2? Positive 2. So, when we look at our calcium plus 2. Our nonmetals are going to gain electrons to get the same electron configuration as the next noble gas. Since they gain these negatively charged electrons, they're going to be negatively charged anions. Again, another term that we're going to talk about next time. To identify our anions, we're going to do the same thing. Our symbol is going to look very similar, where I rewrite the chemical symbol for my element, but it's going to be a -1, a -2, minus something. My example here is ion. Sorry, not ion, iodine. If I look at iodine, iodine's number 53. So I'm going to do a little cheating. I'm going to make this easier on myself. Kr, I'm going to shorthand this. Kr, so that's what? 2, 3, 4, 5. So that's going to be 5s2. 1, 2, 3, 4, 5. 5s2. 4d10. 5p5. We agree with that electron, that shorthand configuration for iodine, right? If we look at my periodic table, iodine's found here. So 2p, 3p, 4p, 5p. 5p, 1, 2, 3, 4, 5. We agree with this, yes? Perfect. So, in this situation, is iodine a metal or a non-metal? You know, I'm quite all right. I can help you. Christina for early dismissal. Yeah, she's packing up right now. No problem. Bye now. Christina, this is homework for you.
Okay.
So, if I have iodine, I know it's a non-metal. My rule tells me that iodine is going to gain electrons to get to 8 valence electrons. It currently has 7. How many is it going to add? How many valence electrons does iodine need to get to 8? 1. So that becomes 5s2, 4d10, 5p6. We'll write that as I gained an electron. So that means I have more negative subparticles. I do positive particles. Minus 1. So I'm looking at iodine. Iodine has 53 protons and normally has 53 electrons. 53 minus 53 is 0. But if I have 53 protons and I add that other electron, now I've gone to 54 electrons. Now I'm negative 1. Whatever I'm losing is going to be plus whatever I'm losing from my metal. When I'm gaining, it's going to be minus whatever I need to get to that noble gas electron configuration. That's what we're aiming for. So let's do one together. I want to look at selenium, and then I'm going to want to look at magnesium. We're going to do selenium together, and then you're going to do magnesium by yourself.
Strontium was repeated, so just cross out the second entry and draw an arrow leading to the first one.
So, is selenium a metal or a non-metal? First thing, type of element, selenium. Metal or non-metal?
Non-metal.
Non-metal, right? We just write Nm for non-metal. If I take a look at my periodic table, selenium is found here. It's found on the right-hand side of my bold steps, making it a non-metal. Selenium is also in group 16. How many valence electrons does selenium have? 6. So, number of valence electrons, 6. So, selenium is going to want to lose electrons or gain electrons? Gain. It's a non-metal. How many does it need to get to 8? 2. It's going to gain 2. If I'm gaining 2, what's going to be my ion charge?
Negative.
Minus what?
2.
What noble gas shares the same valence electron configuration as selenium -2. Krypton. Kr. I want you to try to do magnesium by yourself. I'm going to come around and check to see what you got. If you need help in the header of your table, type of element, it tells you, are you looking for a metal or a non-metal? The number of valence electrons. You should be able to pull that directly from the periodic table. How many electrons will it gain or lose? Metals lose all their valence electrons. Non-metals gain enough to get to 8. Symbol of ion. Losing makes it positive, gaining makes it negative. Noble gas that has the same number of valence electrons as your ion. You need your periodic table for it. I'm going to come around, check what you did for magnesium. Give them a head start. All right. We got some. Nice work. Look at your periodic table. Magnesium is a metal. Nice. All right, let's do the job. Yep, no, magnesium right here. So left hand side. Let's see what you got. Nice work. Good start, good start. She right down and you go first, okay. Okay, good start, good start, good start. Nice to see you. Nice to see you. Good job. So how many rounds? Six. Two. You got some. It's all 2 rounds.
Yeah.
Think about it. All right.
So you did 2 I think it's 2. No. Oh, 1, 2. And then you said 3. I will be doing those 2 because we will go back to 1, 2, and then it's 8. And if it's negative, because it's never been used for instant, then it makes it positive. If you're instant, then it's positive, gain, that makes it negative. It's positive. So 2 and 2 plus 2. I know this. Something's true in wait, so wait, is it because it goes back to where
So, ladies and gentlemen, magnesium. What was it? Metal or non-metal? Metal. Number of valence electrons? 2. So you're going to lose or gain electrons? Lose. How many?
2.
Yep. So, my ion symbol, Mg what?
+2.
Plus 2. What's the nearest noble gas to it? Was it? Neon. So, magnesium, if I flip my paper over again real fast, magnesium goes out to 3s2. 1s2, 2s2, 2p6, 3s2. If these two electrons get taken away, I got my 8 valence electrons right here, right? So I've hit my target. Now I'm looking for which noble gas has 2, 4, 10 electrons. That looks a lot like neon to me. Because of that, it's stable. I'd like for you to finish the other 7. That is your homework. Is to finish the 7. If you get done a little bit early, congratulations. You don't have any homework for the weekend.
You mean the other 8? S, R, F, N.
Well, because there's 2 SRs, right?
No, it's S, R,
1, 2,
F,
3,
N,
4,
P,
5,
A,
6, 7. Oh, there's 8. You're right.
The second SR, just cross it out and draw an arrow to the first one.
Key thing I want you guys to do, I want you guys to wrap this up. And you're going to hold on to it. Put it in your notebook.
Yes, we're holding on to it.
Because you're going to show me your piece of paper next time.
All right.
That's your homework. Now, while we're chatting, I do want to put a couple things in your ear. So, next week, I see you 3 times. Monday is going to be a notes day. Wednesday or Friday is going to be a lab day. On Monday, we're going to see if water can truly conduct electricity. And then we're going to see if covalent bonds. We're going to see if covalent bonds can, excuse me, what type of bonds can help water conduct electricity. We'll get some salt, we'll get some sugar, and we're going to see what they can do. That is what we're going to do Monday. My goal is by Monday we'll wrap up the notes on Monday and we'll have a chance to break off into the lab come Wednesday. So we'll have a full day for a lab on Wednesday. And Friday, I'm not sure yet. Depends on how long it takes us to get through those numbers on Monday. If we get through them all the way, boom, we got a lab Wednesday. If we don't, hey, we finish on Wednesday, that means that we'll probably end up doing the lab on Friday. Make sure you're using your time wisely. As you see, bell rings and 18 minutes. If you get done with the homework before the bell rings, I'd recommend going back and cleaning up the mistakes on your flame test lab that I handed back to you. A lot of people forgot to do the pre-lab and lost a lot of points because of it.